Okay, this is perfect. So basically, you can just go to, you don't have to be here, you can just do your own thing, and they should see that particular screen. You need literally 3 minutes to set up.
Do I need to wear a microphone, or I'm good without? I'd like not to, but...
It's up to you. I think as long as you speak up, that's fine. Are you planning to be close to your computer?
Yes.
Okay, because then I think the Hangout's going to use your machine. So.
So I won't see myself, or I'll see myself afterwards?
So, yeah, it's a weird thing about Hangouts. It's either going to be the screen
Yeah, sounds good.
or yourself,
Yep.
which I figured it's better.
Makes sense.
Just 1 second, sorry. Okay, so it looks like we're right now. So I just wanted to give a few updates about what's coming up. So today is obviously really exciting. We have this presentation and we have Dumi coming, and maybe he'll come out and hang out with us afterwards. We also have on the 25th, like a combined meetup. It's going to be chapter 17 and 18 together, and we have like really good presenters. Dominic is going to be doing Monte Carlo methods, and he's just like a really great presenter. And chapter 18 is going to be presented by Gavin. So he's the British dude who hangs out with us. And that was an area of his research for his PhD. So I'm assuming he knows a thing or two about those things. And then we have a presenter for chapter 20, and we also have a presenter for chapter 19, which I'm especially excited about. Her name is Mimik Su, and she is working for Baidu AI Research Lab. She used to work for Google. She's really cool, and she's the only to-date presenter who is female, so I'm excited, especially for that. Some bad news, still no presenters for 2 chapters, chapter 16 and chapter 13. 16 is coming up next week, and 13 is keeps on being pushed. Somehow it just like linear factor models are not being popular. If by like the end of this week or on Friday, if I don't have a presenter lined up for next Monday, what I'll end up doing is one of the 2 things. So maybe we'll have like an impromptu session, and there's like some exciting possibility. And if this is something that's going to happen, then you'll know. And if not, we'll cancel it and we'll do a combined lecture for like 13 and 16 together. Yeah, sorry guys. Fine, but it's not as straightforward as one would want it to be. And with this much said, I think we are ready to go. So Cosmin, whenever you're ready, take it away.
Cool. Thanks. Hey, so my name is Cosmin Negruseri. I'm a machine learning engineer at Memo AI, and my interests lie in NLP, information retrieval, and algorithms. Today we're going to go through chapter 15 of the deep learning book, which talks about representation learning. Some of this material was already done previously, as representation learning is closely connected to deep learning. Quick note from my startup. So we build Memo, which is a wiki for Slack teams that's always up to date. Memo is great for quickly saving onboarding information, meeting notes, DevOps instructions, or links. Your information will always stay fresh, as Memo will smartly remind you of content that got stale. Okay, with that said, most of my slides are taken from Joshua Benjo's past talks and tutorials on representation learning. There were no slides on the deep learning book website. So why do representations matter? This is an example earlier in the book where we need to separate green triangles from blue dots. You can see that if we use Cartesian coordinates, it's not impossible to separate them linearly. While if we switch to polar coordinates, it's straightforward. Another example in the book is doing long division. If we would use Roman numerals for long division, then it's going to be really hard. And most people just switch to Arabic numerals. So this Venn diagram from the book tries to tell us that deep learning is a kind of representation learning, which in turn is a kind of machine learning. Note that for representation learning, we have shallow autoencoders as one way to do representation learning, but they are not part of deep learning since they're shallow. So again, an example from the beginning of the book. Here we have to do a classification task. We have to classify what's in the image. If we would use the pixel-wise representation of the image, it's not really easy to figure out what's in that image. So neural nets go layer by layer and learn more abstract representations. In the first layer, we get edge detectors like vertical, horizontal, diagonal. Then on the second layer, we start learning like contours and corners. And on the third layer, we start getting parts of objects like a wheel, face detector. And then finally, we can use those third layer features to build a classifier on top of them. An interesting side note is that we might use the activations at the top layer to find similar images. So basically, we would find a similar image by finding other images with similar activations on the top layer. The book goes through this greedy layer-wise unsupervised pre-training algorithm, which is was a pretty big deal when it appeared, and it's kind of a long name, so we're gonna discuss through it. Before, deep models were really hard to train because the signal wouldn't get propagated through to the start of the network. So deep learning wasn't very popular for a long time. But in 2006, there's been this deep learning breakthrough where Geoffrey Hinton in Toronto managed to train deeper models. Followed soon by Joshua Benjo's group in Montreal and Jan LeCun's group in New York. But they're all based on the same kind of idea. What Geoffrey Hinton did was he used the stack restricted Boltzmann machines. I guess we're gonna cover restricted Boltzmann machines in one of the next chapters. So I won't go through that. But I'll go through a similar idea that uses autoencoders instead from Joshua Benjo's group. And this idea has the advantage that we already covered autoencoders in the last lecture. So a refresher on autoencoders. They learn representation learning, and so how do they work? You can see here, you get an input, you have one hidden layer, and then you try to reconstruct the input going through that hidden layer. One way to make sure they learn something useful, not just the identity function, is to make the hidden layer smaller than the actual input. They're also autoencoders are also a way to do dimensionality reduction, but as opposed to SVD or PCA, they're not linear because they use these nonlinear functions in the middle. So everyone's clear on this? Okay. Okay, so let's go through the long name algorithm. So you get the input, and then you want to learn some features. How would you learn those features? Well, we would use an autoencoder and try to reconstruct the input. So basically, we can learn the weights on the first layer and find some good weights that can reconstruct the input. Then next, once we figure out some good weights, we freeze them, and we want to learn more abstract features. So how would we learn these? Well, again, we use an autoencoder, and at this stage, the autoencoder needs to reconstruct the activations at the first layer of the input, so basically in the feature layer. And then we can learn even more and more abstract features by training an autoencoder at each layer. Once the unsupervised, note that the previous steps were all unsupervised training. We didn't need any data labels. We just needed images. We didn't need to know what's in those images. So once we're done, we can add a linear classifier on top of this network and use the supervised data, basically use the labels. So we can see what the network would guess and then use backprop to fix the errors. So this step is called supervised fine-tuning because we already have good weights because autoencoders do good representations. And then we tune them so that the whole network does well on this specific task. So any questions on the algorithm? I guess everyone, go ahead.
How do you decide the width of the activation layer and the height?
I think I'm going to go a bit through this later. I think it was an art, so yeah.
So you still have this problem with disappearing,
vanishing gradients. So basically, since at each point you train just one layer, there's no disappearing gradients. You can train that one layer because everything built. Yes, but if your weights are already very good, then you don't get so much of the vanishing problem. And that's basically the breakthrough, that the weights are already very good, and they were able to learn more than one or two layers. But that's a good question. Thanks. Okay, so let's go through the name. What does pre-training mean? Basically, there's two phases, one of pre-training and one of fine-tuning. And unsupervised, you saw that each time we used an autoencoder, we didn't need the labels. We just used the reconstruction error to train. Then layer-wise, we go layer by layer. It's greedy because each layer minimizes its own loss function, independently of the whole network. So when and why does this unsupervised pre-training work? Around 2009, Dunitru Erhan, who is going to come later, I hope, and a team in Montreal did extensive experiments comparing supervised training and unsupervised pre-training and fine-tuning. You can see on the left the test error on digit classification using supervised training, and on the right, the test error using unsupervised pre-training and then fine-tuning. You can see that unsupervised pre-training is much better. Also, a thing to note, for supervised training, we get the best error for 2 layers, and the more layers we add, the worse the network gets. And they actually mentioned that for 5 layers is even worse, and so on. Another note is that in 2009, Deep Network had around 5 layers. Go ahead.
There's people online that are saying that it would be nice if you are pointing out something, if you could move the cursor there, like not right now, but apparently that was a thing sometime in the previous slides.
Okay, I'm gonna try to explain a bit better which areas of the image I'm looking at, but it's kind of hard to. Thanks. Okay. So this is a graphical representation of the experiments Erhan et al. Ran. Basically, the weights of each network are projected in 2 dimensions and visualized using t-SNE. It's a popular visualization method. The color indicates the training time. So each point corresponds to a different neural network at a particular training stage. You can see the 2 clusters are pretty separated, and that means that the training weights of in the supervised case are in a different space from the unsupervised pre-training case. There's another visualization in here, which instead of using t-SNE for projecting network weights, t-SNE is a kind of local, preserves local locality, but doesn't preserve distances. And this visualization called isomap preserves distances, so in a sense, they preserve relative volume. We might draw the conclusion from the graph that pre-training minimizes the variance of the training, since you see that in the non-pre-trained case, the training things are much more scattered. So in 2010, there were 2 hypotheses why unsupervised pre-training helps. One was that the representation, which is good for the data, is good for telling us something about the labels of the data. And the other one was that it helps with optimization. The fact that it helps with optimization doesn't seem to be correct in 2017, since we can train really large networks now. Go ahead.
Just one question. So you stack up the output pointers. Are they different or they are the same?
I think they are the same. You might basically that's a problem with this this approach. I was going to go through it later, but each layer has hyperparameters and the decision of the architecture. So, like for a big supervised network, you already have to decide on the architecture and the hyperparameter, but you have just one set of hyperparameters. While in here, there's all these decisions you have to make. I guess Dunitru can tell us more about these exact experiments and how the architecture looks. Go ahead.
What exactly does he mean by function space on the X and Y coordinates? Is that really a compressed, the weights compressed into 2 dimensions?
Yeah, so there's a dimensionality reduction of the parameters of the network. Sorry, I'm smiling because Dunitru can answer better.
It's actually not the parameters of the network, it's the implicit. So that's the function space.
Okay, so the activation.
The activation, well, the block is because otherwise the parameters themselves, many networks that have different parameters but the same output. So you want them to have the same.
Okay, so in 2012, or before that, Google did a big experiment in this greedy layer-wise unsupervised pre-training thing, and they built a huge model with 1 billion parameters. They trained it using 16,000 CPUs in 3 days, over 1,000 million YouTube frames. And once they did that unsupervised pre-training, they run, I guess, supervised fine-tuning on ImageNet data, and I think they got state-of-the-art performance. So, go ahead. I think, I don't know the detail, maybe 10H or something like that. But that's a leading question, because soon after the Wired results, I think there was an ImageNet competition, and Geoffrey Hinton's group in Toronto, I guess, managed to train on ImageNet using just 2 GPUs, convolutions, switching from 10H to ReLUs, and adding dropouts. I guess dropout was the new thing in the that wasn't published before. And they trained over 11 layers, and they trained So they got much better performance than the big Google system, I think. I'm not sure. Go ahead.
The book says modern techniques. You don't need the unsupervised pre-training.
So that's exactly it. This one is you just get the images with the labels. 60.
So is it the ReLUs that eliminated the vanishing gradients, or what aspect of this approach solved the vanishing gradients with 11 layers?
So probably Dunitru can explain better. I think ReLUs were really good because you get this when in 10H, from what I understand, if you're in the wrong side of the sigmoid, it's really hard to go to the good side. So because you don't have any gradient around there. I think they also did much better initialization. And dropout helped a bit. And one important thing was that they used convolution. So basically, they had much fewer parameters. You can see here they have 60 million parameters, while in the big autoencoder network is 1 billion parameters. I think that used some dense layers, while this one, so a convolution versus a dense layer uses an order of magnitude less parameters. Okay, so after being able to run this network over the entire image data and get great classification performance, greedy layer-wise unsupervised pre-training is no longer as popular. So, Dunitru, there was a question earlier about the architecture of these autoencoder networks. If each layer has to have the same size or different sizes, or
It doesn't have to. I think that's fundamental to any result.
so to me, like I was trying to read on Quora why there, and someone said like there's just deciding hyperparameters, maybe learning rates or architecture might be too much work.
I think most people doing this pre-training terms, they just choose the same with all the layers because it's just easier. Fewer things to think about.
Do you have to use different learning rates, or it's the same sizes of?
I mean, now maybe I think in theory you should use a learning rate where you can have a also everything.
Okay. Oh, thanks.
So there is no multiple layer. All the layers are the same size. So how do you work?
So there's more variants of autoencoders. I don't know which ones were in your paper. I guess you can do sparse autoencoders or denoising autoencoders. So there are different ways to kind of do a bottleneck. So the ones I explained there.
That's the same weight. With the same
Weights. I'm not sure what that would give you. I mean, you could if you want to learn. Because the original input is as, in this case, it's like a much pixel. So you train an autoencoder that projects the kind of representation.
Exactly. So from the first layer to the second layer, you already go from images to activations. So you no longer reconstruct images, you reconstruct their activations, I think.
But at the same time, I mean, you have this small layer on the first layer that you use. That when you train the second layer, already what's the presentation?
Slightly worse, but still they should do good representation even. I mean, they learn edge detectors in the autoencoders, and then once you learn the edge detectors, you can kind of reconstruct using edges and stuff like that. So it's not really worse. It's more abstract and more abstract the higher you go, I would guess. Okay, let's go on, because Dunitru can, I think I have a few slides from his paper, and he can tell us more about it, but we have to cover a lot. So these are the experiments. These are the training trajectories. Okay, so cat detector. So there's been a recent paper that was saying that recurrent neural nets are hard to train if they're stacked on top of each other. So people there were trying to do layer-wise pre-training, or maybe layer-wise supervised training, which is kind of funny that the technique never gets old. Okay. So Humans learn from few examples because they can transfer from one task to the other. You don't need to see, like in ImageNet, 1,000 images of an elephant to understand the elephant concept. You can transfer what you learn to a different context. So how would we do that with neural networks? One way is multitask learning. We could train different tasks with the same kind of input and reuse their intermediary representations. For example, in image classification or object detection, we need edge detectors in both of them. So we might be able to reuse a common trunk and then fine-tune on the different tasks. Another concept, the related concept, is domain adaptation. An example in the book is sentiment analysis. You might do sentiment analysis on movie reviews or on restaurant reviews. And you have the same task, but different kinds of inputs. The vocabulary, I mean, the total task is the same, but the vocabulary might be pretty different. So supervised transfer learning is very popular on images. Training big models like VGG or Inception, ResNet take on the order of weeks. So if we use a pre-trained model and then fine-tune to our specific image recognition task, we can get a great quality classifier even if we have very little data. I think it's used a lot in the industry. It wins Kaggle competitions. And it's used as a building block for image captioning or visual question answering. It might not work well when we have data distributions that's very different from ImageNet pictures. For example, it works well for detecting skin lesions or cancer cells, since the data is pretty different. So zero-shot and one-shot learning are extreme examples of transfer learning. One example task for zero-shot learning would be to recognize a new object given only its textual description. So in this picture, we can see kind of an idea about how zero-shot learning might work. We have the X space, let's say the image space, and the Y space, the description space. And we learn representations for the image space, hidden representations. For the image space and for the text space. So if you learn a mapping between the hidden representation of the image space and the hidden representation of the text space, then we might be able to go from a textual, for a new example, from the textual representation to the image representation and get from the representations to the actual real examples. Hope that makes sense. There's an impressive result from Google multilingual neural machine translation system where they actually do zero-shot translation. In a classic translation setup, you learn how to go from one language to another language. But Google built a single translation system. It trained it using Japanese and English pairs, and English and Korean pairs, sentence pairs. And then they were able to go from Japanese to Korean and back, which is super cool. With pretty, sorry?
No more training to do that?
No, so they just use English, Japanese, and Korean English, and they didn't need any additional examples to do a pretty good job at Japanese to Korean and back. So here's the kind of architecture of the network they used. It's kind of, it has an encoder, it has a decoder. Each have 8 layers of LSTMs. And note that the input for the encoder has the special token, 2ES, which means to Spanish. And then the network gets the input, it goes up, it encodes it, and then using attention and the encoded input, it sends it to the decoder, which manages to decode it in Spanish. Any questions so far? Okay. The book goes over disentangling causal factors in semi-supervised learning. semi-supervised learning might work if the labels have some correlation with the distribution of the data without the labels. An example is a distribution with 3 bumps. We might need just one example in each bump to tell us about the Y label. But if a distribution would be uniform, we couldn't tell anything about P of Y given X. Here's an example from autoencoders. So autoencoders usually use the mean squared error for reconstruction. And in this example, you can see that the reconstruction loses track of the ball in the image. Go ahead.
It's not a, it's the Y that causes the cluster.
Sorry, this part of the chapter I'm not very clear on either. Yeah, so here the kind of the representation that the autoencoder does loses track of what's important in the image because there's a small object there, and the mean squared error loss kind of loses track of the small object. So basically, the representation doesn't understand the objects in image. A way to solve that is using generative adversarial networks, which basically learn the loss function. Does this picture look natural or not? So this is kind of a longer topic, but the idea there is that we train a generator and basically a generator and a discriminator play together. The generator starts from a noisy vector, it generates an image, and then the discriminator has to tell if that image comes from the generator or comes from a data set of normal images. The more they play, the better the two get at discriminating and generating. So basically, they learn how the distribution of natural-looking images look. Here's an example. Here's a comparison between so the task in here is predict the next frame in a video. On the left, you have the ground truth. In the middle, you have autoencoder prediction, and on the right, an adversarial network. So you see with the mean squared error, the low contrast here disappears, and the image is a bit more blurry, while the adversarial network figures out what's important and keeps the ear there, and the image looks a bit sharper. So basically, GANs are better in capturing salient features in images. So the chapter goes through distributed representations. Why are they important? So they help us deal with the course of dimensionality. If our data is one-dimensional, we might model it using a histogram. So we split the data domain into boxes, and for each box, we have a separate prediction, like, for example, the median value in that box. When we go to 2, 3, and more dimensions, a lot of boxes will start to be empty, so we won't have good predictions for them. So previous shallow models rely on locality to cover the data domain. Nearest neighbors assigns a region to each point. The number of these regions is proportional to the number of parameters of the model. So basically, it's the size of the model is linear in the input and in the number of parameters. But if we switch to also the space is totally partitioned and all the regions are disjoint. When we let regions not be disjoint and learn independent features, we can have more expressive models. You can see on the bottom a small network with 3 features. Let's say feature C1 represents the concept of glasses or no glasses, and C2 represents the concept of a man or a woman. Using these kind of features, we can learn the concept of a woman with glasses without having to see this example in our input. Also, if each of these features splits the space in 2, we can get 2 to the power of n minus 1 regions instead of n regions in the shallow case. We can see that this actually happens for generative adversarial networks. Here we do vectorial algebra on the image representations. So a man with glasses minus a man plus a woman gives us a woman with glasses. And I think in the data set there was no woman with glasses. So basically, the glass concept was learned independently. So independence is great, but compositionality and hierarchy is also useful. There have been some theorems that shallow models are good enough to learn any complex function, but in fact, they require an exponential number of features. This was one of these theorems are one of the reasons that SVMs were popular and deep networks were not for a long time. In the book, there's a few examples that show that we do need deep models. And here's an example where we can learn complex polynomials in multivariables using low effort. For example, here we can see that x2 times x3 is computed only once, but used in a lot of places. Also, when we kind of flatten out the polynomial represented at each node, it's exponentially long. So we still have from this presentation a nice theoretical result by Răzvan Pașcanu and a group in Montreal. And a cool metaphor for the expressivity of neural nets. So a rectified linear unit is a simple function which for negative x returns 0 and for positive or equal to 0 returns x. It's a piecewise linear function. When we build a big neural net, we compose these piecewise linear functions, and we get still a piecewise linear function. So the more pieces in a piecewise linear function, the more expressive the function is. So we can learn complex functions if we have a lot of pieces. So one way to approach the complexity of a deep learning model is count the actual number of pieces for a deep versus a shallow model. Here, Răzvan goes over a shallow model. So each rectifier basically splits the space into half planes, where you have x on one side of the half plane and 0 on the other side. And he uses an old theorem which tells us in how many regions these half planes split the space. Now he goes through a deep example. Instead of using a rectified linear unit, he uses absolute value as a nonlinear activation function. So in 2D, the absolute value maps these 4 points to the same point in the first quadrant. Now he goes through the example of what happens over a multi-layer network. So on the first layer, you move all the 4 quadrants to the same quadrant. And then again, once you are in the top quadrant, you might have negative biases in your activations. So you move the values to have some negative values, and you can fold again to the first quadrant. Note that at the last step, you might get a separator function. If you go back and unfold everything, you can see that partition function maps to the initial input, and for a really nice pattern. So basically, learning neural nets is like folding a piece of paper, and the more you fold, the easier it is to separate the two two types of points in the data set. Using this approach of counting the number of regions and the previous results, they got the result that deep networks have an exponential number of regions if you count the number of layers. So they're exponentially better than the one-layer models. I think that's about it. Any questions? Okay, thank you. Go ahead.
Philosophical question. Is there ever a problem? Representation is really short, right? It's fixed length. So try to describe different sized objects always have the same size effect. At some point.
I think people use big enough vectors so that, I mean, there's a trade-off in the speed of the training and the size of the vector. And they probably do need to be dense because GPUs need to be able. I mean, they work better with dense vectors, or not sparse. Yeah. Thanks. I guess Doom is next. Sorry.
Thank you.
You want to do an introduction, or I could do one?
You should do an introduction, but let me do this thing. I'll stop this.
Did you prepare slides for me?
I have some backup slides.
So I'll just let people see the presenter, but do you want to do it properly?
Oh yeah. You want me to be
So yeah,
in there?
probably over
Okay,
here
okay.
because. Yeah, so Dunitru Erhan is a senior researcher in Google Brain. He did his PhD in Montreal with Joshua Bengio. He was part of the team that won ImageNet, the ImageNet image classification competition in 2014. He worked a lot on unsupervised training, on image recognition, object detection, image captioning, and a lot of other things. You saw his paper previously in the presentation, and yeah, I think his image captioning paper was one of the first that used neural networks to do that. Maybe I'm wrong, I don't know. But yeah, it's awesome that we have him here today. Thanks, Dimitri.
You can ask me whatever you want. Sure.
Yeah, is it safe to say, up to now, the greedy layer-wise training, pre-training is gone, or that someone brings back later?
So I think the strictly speaking, yes, what you're saying is correct. I think the greedy layer-wise pre-training is gone, but the unsupervised pre-training part is maybe not gone. So there's a lot of people still doing that, but maybe not as much in vision domains. So there's a lot of, I think in NLP, sort of natural language modeling, people do pre-train on the word embeddings. I think in speech maybe that also still works to some extent. I don't quite follow necessarily all the domains and what is the state of the art. But yeah, I don't think people really do the greedy layer-wise pre-training part anymore, and I don't know if it will come back. It's hard to really say what will work.
Yeah, can I continue with another question?
Sure.
I'm also a little bit confused about the logic of the book's chapter.
Oh.
They started with this greedy layer-wise pre-training says that representational training is very important for deep learning.
Mm-hmm.
And then it says, okay, this one is not used anymore.
Mm-hmm.
And then from there, I sort of think, okay, the reason we want the representational training is for eventually for deep learning.
Mm-hmm.
But then somehow it keeps on talking about this representational training. Well, right now, why do we have that? So it's for the zero data learning, or in what context are we using that, including the generative velocity networks? So
there's a lot. I mean, my answer will be a bit long, but sort of I think the idea of greedy layer-wise pre-training was to enable deep learning to some extent, right? So we knew that we could have deep networks, right? I mean, that was not a mystery, right? We just didn't know how to train them, right? I'll come back to why we want representation learning in a second, but assuming that this is what you want, which is we do want to do better representation learning, and if you believe that deep networks are a solution to that, then you wanted a way to train deep networks so successfully, right? So, and we didn't know that in like 2005 or 6 how to do that because we were using sigmoids and and didn't have dropout or batch norm or whatever. So greedy layer-wise pre-training was one of the solutions for that. It turns out that it's not necessarily a useful solution anymore because we have all the other stuff that makes whatever vanishing gradients not as big of a problem. Just saying feed-forward networks. Now, why is representation learning still useful? Because we already know how to train big nets and that are deep and have 1,000 layers or whatever. I think not all the problems can be cast as sort of ImageNet or where you have a lot of label data. So you still want to be able to do kind of, as Cosmin was saying, you still want to quickly adapt to a new task. So I think a lot of the sort of state-of-the-art research in machine learning and deep learning in particular is to figure out how to enable this representation learning of these representations that are easily transferable to other tasks. So zero shot maybe is an extreme case of that, but maybe not so extreme. So so I think that's definitely one of these cases.
How is that different from the transfer?
It's not. I mean, I think this is like between like multitask learning and transfer learning and domain adaptation. There's some, they all have their own strict definitions. I think it's helpful to think about it this way. Domain adaptation is you have the same label space, but maybe different kind of input distributions. So you train an ImageNet cats, and then you point your ImageNet classifier with webcam images. That's very different, but it's the same domain, right? Multitask learning is if you're training both on recognizing cats and whatever, cancer detection. I don't know why you do that at the same time, but maybe you want to do that. And then transfer learning is, I don't know, you transferred your cat versus dog classifier into a dog breed classifier. So they're kind of related, but they're not the same domain and stuff like that. So, yeah.
Chapter said there was a modern approach of doing simultaneous supervised and unsupervised learning instead of the sequential stages.
Mm-hmm.
Could you kind of explain briefly how that?
I mean, it's just composing those two losses at the same time, right? I think it's summing them, right? So I think that's not. It's not super advanced. It sounds more fancy than it actually is. So if you have a supervised objective, which is to minimize the log likelihood of the correct class, plus the unsupervised objective, whatever that may be, a reconstructing loss or whatever. So you just jointly try to minimize those two. I think that's most of these semi-supervised approaches. That's what they do.
Some of your input data would have a label, some of it wouldn't have. So how does that?
Right. So you would try to. There's a bit of a kind of alchemy / black art in there, right? So how do you update your parameters, right? So for those inputs that have both of them, all your inputs have an unsupervised. If they exist, you can use an unsupervised objective to update the parameters. Some of the inputs will have both. They'll have a supervised label, and you can update do the unsupervised objective minimization. How you trade off these things? Again, it's a research paper, so I wouldn't. But that's the general framework. It's just you have the two objectives and you try to minimize them at the same time. Subject to the fact that you do want, ultimately what I think you mostly care is the validation error of this model on the task of interest, right? So in some sense, you don't want to completely ignore the supervised costs, right? So it's there to guide the unsupervised learning objective into maybe doing a better representation learning to uncover some sort of better hidden factors in your data. But ultimately, the goal is to do better supervised learning. Yes.
Before we move on to the
Okay.
question, would you mind repeating the questions? Because
Oh yes.
people
Okay.
might-
Sure.
Can you tell us about how practical are second order methods for training beyond?
So the question is how practical are second order methods beyond stochastic gradient descent? I'd say. So KFAC, yeah, I think the more classical sort of second order methods like LBFGS or something like that, they're not particularly useful, I'd say, in sort of large scale deep network kind of community. I think if you have a very small data set, maybe, but I'm not sure how well that network would generalize in practice. I think KFAC is a promising. From what I know, I'm not intimately familiar with KFAC, so I don't want to answer for the KFAC authors. But I think that's a very promising direction. So I think you should look into it if you haven't. Yeah. But SGD is definitely still or RMS prop Atom. I think that's what most people use. 99% of all the people's trainings is done with that.
And if there's like convolution, that's the only.
Yes. I think there's been some sort of questions about convolutions if that's the only way to go still. instead of like second order methods. Yeah, there's some, I think the people have reported some success with using Hessian-free sort of methods for training RNNs regarding neural networks. I don't know how well those results generalize. So yeah, I think there's some paper by Elias Uskiver. I don't know what. Maybe Yaroslav knows this better. He was looking at this for a while.
It seems I hear people, hearing people say that it's hard to reproduce all those Hessian-free methods.
Yeah, so that's, yeah. The reproducibility of a lot of these results or generalizing them to more than one data set is a big problem, I'd say. So that's why, that's why most people stick with ADAM or RMS prop, because that usually works pretty well. So, and it's hard to beat. So. Go ahead.
I actually wanted to ask, what is the current state of the art of semi-supervised?
I think ladder nets, maybe. But I don't know what it depends on the context, I'd say. You mean in like ImageNet style thing or CFAR10, something like that? Depends. I think semi-supervised learning has a bit of a problem of like defining what's a good benchmark. There's no like ImageNet of semi-supervised learning, or there is if it's very, very crappy. Like I think there's like some subset of CFAR10 or something like that.
So actually, what I wanted to ask is, think about things like distribution speed and sampling.
Mm-hmm. Yes. Oh yeah. I've seen temporal and sampling. Yeah.
And my question is it possible to do that after observation?
I mean, you can view everything that trains a neural network as representation learning. Yeah. Yes. I think the temporal assembling, if I remember correctly, yeah, it's a whole. I don't know, like at this point in time, which is the state of the art. But yes, temporal assembling, I think, was state of the art at some point in time. Yeah. Anything else? Yeah, as I said, I think that the problem is defining concretely what is a good benchmark there. Like how much unsupervised data to use.
So what is the representation?
I mean, it's the same representation that you're learning in a supervised. So in the computer vision community, I think people have this more of an idea that you're going to learn some feature extractor using some data set, maybe ImageNet, maybe Pascal, or whatever. And then you're going to apply this feature extractor to your labeled set of interest and train some SVM or whatever on top of it. So that's sort of the computer vision recipe for semi-supervised or learning. And that's sort of, they've extended that from using SIFT or whatever, HOG, from the more classical computer vision kind of techniques to using now VGG inception. So they treat them as these like black box feature extractors. Some more advanced computer vision people will fine tune those feature extractors on the task of interest. But that assumes that you have labels in the task of interest, or a lot of them. Because if you have the VGG, you can't really use 5 labels per class. So, yes.
So a while back, Vincent van Gogh said that ImageNet is the new MNIST and that we shouldn't do any more research in it. We need a better data set that's more worthy. Is there this better data set?
So the question is ImageNet the new MNIST? Should we be doing something else? Yes. And yes. Is there a better data set? Depends on what you care. I think some people think that the MS FOCO data set, so if you don't know, this is sort of named MS FOCO because none of the people who created it, I think, works at Microsoft anymore. They all left for Facebook. But it's this not as big as ImageNet, maybe a few 100,000 images, but it's labeled with instance segmentation masks, so it's pixel-wise, kind of, what is this class? It has like the image captioning data in there, so they're just kind of natural language descriptions. I think a bunch of other stuff, and then they run an annual competition where you can like train your object detector to do like instance segmentation and stuff like that. And it's a much more challenging task. Certainly, it's nowhere near perfection, the current state-of-the-art models. There's some, you may argue that, I don't know if that's still as interesting in terms of, depends on what your ultimate goal is. I think if your ultimate goal is to build the best object detector, this is a great kind of test bed because they have a few very strict metrics and as to what qualifies as a good model. So if you want to predict like a cat, it better overlap a lot with the actual cat in the image, because they've exhaustively labeled all the pixels with all the classes that are there. It's actually a meaningful thing. The problem with that data set is that it has like, I think, 80 categories. There's somewhat haphazard, kind of really random, like there's like zebra and traffic light, or whatever, bottle, I don't know. I don't know how much people care about that specific subset of, and it's the same with the image captioning data that you have in the data set. Like if you ever see any of these like image captioning models, you apply them to a real image, they'll always talk about school buses and zebras, because that's what the model was trained on. So it only sees that. So, I would say if you really want sort of to advance deep learning and whatever, you should look at like more data sets where there's like interaction with the one, like the robot pushing data set from Chelsea Finn and Sergey Levin. Any of these sort of like things where there's an agent that is interacting with the world and there's a reward and whatnot. But those are much harder. And it's harder to get like a uniform benchmark that is as clean as the machine. You had a question? SSD versus YOLO? They're the same, basically. Yeah. SSD versus YOLO. Yeah, okay. Those are two object detector methods. I was part of the SSD effort. There's this nice paper by one of the groups at Google, headed by Kevin Murphy, and they compared all of these like faster RCN and YOLO 9000, and they put them all in this like cost versus benefit kind of curve. So you can, if you're actually running object detectors in real life, you do care about like how many CPU cycles you can afford per image. So you can say, okay, I can afford this many CPU cycles, and then you can, once you fix that axis, you can choose which one of them is better. So there's no object detection model that is both the fastest and the best, as far as I know. Yes. So, so I didn't understand the beginning of your question. I'm sorry. Right. And you have labels. So the question is about like detection with thousands or tens of thousands of classes, and you assume that you have labels for those tens of thousands of classes. I mean, the SSD YOLO-like approaches are not too bad in that respect. You could always, I mean, if you have some structure in your classes, you can always do some sort of hierarchical kind of two-stage approach, where if you have like have dogs and dog breeds, usually you don't have like tens of thousands of course classes, I'd say. So they can be usually subgrouped into more meaningful chunks. You could also think of doing, again, depends on the computational budget, right? So always do a sliding window approach. You just apply a classifier at every scale and every location. So if you have not that many images and a lot of CPU, yeah. Otherwise, you can, if you have like millions of classes or whatever, billions of classes, you can always do what the FaceNet approach. So where you train an embedding, and you do nearest neighbor in that embedding, stuff like that. So, yes.
Is there some interesting work on combining data cascade?
So you mean like having a reject class kind of thing, and sort of?
So kind of like in the village with
I mean, you can do that even now, I think. I mean, you can train. So the question is about, can you do like Viola Jones style cascading of results where you can sort of have a high recall classifier, some sort of in the beginning that kind of rejects the obvious things and the obviously easy things, and then these sort of narrows down the. You can still do this now, right? So you could train like one network that is doing the easy filtering. So, and they just optimize its operating point to something that's high recall. And then I think the problem with that is that it's a lot of work to kind of engineering work to do this. So I think it's a very task specific thing. I haven't seen like a principled approach to do this, but I must say I'm not. I may have missed it as well. I think that's probably something that people in like at CVPR, if you're looking at any of these like proceedings of that, they would probably be very much into that. So. Yes.
How do you assess the outputs learning for accuracy? It seems like they really don't know what's coming until they output something.
Right. Yes, it's a good question, and you know I think I skipped a bit the chapter. It also touches upon that a lot of this greedy layer-wise unsupervised pre-training suffers from this, where you don't know if you've learned a good representation until after you've like done the supervised learning and tested it on the validation set. So, and I will repeat the question for the posterity. That is, how do you assess the quality of representation learning before you actually have some supervised signal? And this is where this sort of joint learning of objectives does help you, because if you learn both the supervised objective and the unsupervised objective at the same time, then you can assess the quality immediately, basically, because you can have some parallel process that takes the snapshot of the model, computes the validation accuracy, and tells you how good the model is. But I don't have a good answer if you have a two-stage approach. So.
Maybe we discussed last time what are good architectural choices for denoising
architectural for denoising autoencoders? Oof, I'm not sure. Do people still use that? To pick noise, I don't think it really matters that much what kind of noise you pick. To be honest, I think I remember there was like one of Yoshua's master students did her master's thesis on just like exploring hundreds of noise types for denoising autoencoders, and do they matter? And I think ultimately they all kind of do the same on MNIST.
Does anybody use them to estimate score function?
The question is if anybody uses them to estimate the score function gradient. I don't know. I'm not sure how many people still use denoising autoencoders, to be honest. So I'll say that. So maybe people still do that in speech if they use fully connected networks, but not in. I don't think people use that necessarily in a principled way as you imply it.
I have a question from the
Okay.
web. So somebody's saying triplet loss seems like a great idea as it forces network to learn good representation, but why doesn't it converge well with SFGTs? Is there a better way of forcing network to learn good representations?
With SGDs, is that what? I think, in my experience, it converges pretty well with SGD. But I think, but this is all depending on that. I think there's a bit of subtlety in all these triplet loss formulations as to how you choose the negatives when you create these triplets. So the triplet loss, for those that are not necessarily familiar with this, is that you, instead of learning a mapping from input to a class label, you form these triplets of like an input, a positive input of the same class, and a negative input of a different class, and you're trying to make to learn the representation that makes the anchor input and the positive input close to each other, and the anchor input and the negative one far from each other. Right. So you try to learn this metric, this embedding, where this is satisfied for most of your data set. Now, it turns out that empirically, if you actually choose always like a very easy negative, you're not going to learn anything interesting. Or if you choose a very hard negative, it may also collapse. So it's always worth it to choose a negative example from a different class that is close somehow to the decision boundary between the positive and the negative. And that by necessity, you have to do this somewhat on the fly. So the FaceNate paper actually discusses this quite a bit. So maybe this is why SGD doesn't work for this particular person, because it will collapse in sort of non-trivial ways if you're not careful with how you choose your negative examples. And the further you are in the training, the harder it is to find these kind of examples that are on the verge of being good or bad. Yeah, question?
I have a few thousand sample images, and you're looking at how close some images are in the representation. And then when I just run it through the the feature network and compare the distance to those vectors, it looks okay, like the images examples are close enough. Because I have no ground truth to say which is really close images, how would I go about improve this process to learn a better representation of these things?
So, well, if you have no ground truth, then I'm not sure how you can learn anything meaningful except for using the pre-trained networks and just using that. I mean, yeah, that's basically, you would need to label some images, I think, in order for either by eye or you could always take up a few pairs of images and say, yes, I agree that these are close to each other, or no, I don't agree that these are not close to each other, and then you can run like a label propagation algorithm, something like that, right? That's the kind of one way of doing unsupervised, semi-supervised learning, so where you create this kind of graph and you propagate labels to the nearest nodes in the graph. And that will maybe give you some meaningful bootstrapping way. Bootstrapping not in a technical machine learning sense, but bootstrapping. So to bootstrap the next round of your triplet loss kind of training.
So follow-up question. So if I label them as what's close to each other, what's not close to each other, some sort of a score or music, right? Then so learning that as part of this representation, try to reduce my representation of these two images are close to each other versus what the
So is your question like if you introduce the labels that you deemed they're close to each other or not, do you co-train then the representation using those labels? Yes, I think that's what I was suggesting. If I understood your question correctly. I'll take Yaroslav.
Okay. Do you have any progress in using neural networks for image or video compression?
I mean, besides the TV show,
Which one?
Silicon Valley. The question was about TV image compression.
Already.
Is there anything that I don't know if it's public or not? So there is progress. I don't know if we put out a paper or not. I'm not part of that. So. The question was about, is there any progress in image or video compression? I know that people are interested in doing that. I think there's this notion of efficiency. So I think certainly, from my understanding, is you can get better compression than JPEG, whatever, 2000, using neural networks, but it's not going to be nearly as fast, or as good. Won't have as good of a memory footprint as your whatever DCT based. I don't know what JPEG 2000 is based on. Yes.
Yes, in your experience, are there like domains or combinations where defense is not considered as like amount of available label training that is not enough, or it's too small, or you want like the high sort of speed of instance compared to say SVM or Cosmin or other.
The question is, are there any domains where deep networks are not the right answer? Specifically, if there's any noise or whatever. Probably. I mean, if you have like if your data is linearly separable, then you should not use a deep network. It's a linear classifier. I think a lot of the more mixed feature kind of kinds of examples where you have like ordinal type of data or categorical, et cetera, as input features, you may be better off using something like a boosted decision trees or whatever. I think a lot of the Kaggle competitions are one like that. So yes, the domains where deep networks are not the right answer is Kaggle competitions. For maybe reasons that are not the right ones. I think in a lot of these domains, it's still useful to have deep networks as an underlying feature representation that so you extract features with deep networks and you use them among many other features in your linear classifier. So a lot of people do that. So it's almost always useful to have a variety of kinds of features in your big model. If you're doing, say, I don't know, CTR prediction for ads or something like that, you'd probably use a diverse set of features rather than just those are extracted by deep networks. I don't think necessarily noise is a big issue. No, I don't think deep networks suffer more from noise than any other class of models. But it depends really on the kind of noise. It's hard to make really sweeping generalizations about that. Yeah, I'd say otherwise, if you have very few labeled images per class, I mean, it's an active area of research. What do you do in general? I mean, deep networks may not be suitable for this, but I'm not sure what else is suitable for this. Short of making very, very big assumptions about the domain itself. So, yeah.
So if you have, like, say, very large short-term translatable, say, text classification, then for sentiment analysis, is that better?
Maybe, but I think sentiment analysis is I was under the impression sentiment analysis is handled pretty well by deep networks as well. So, in fact, I think I just saw a paper today about sentiment analysis where they were using unsupervised pre-training. So, but I think again, it's one of those. It's the sentiment neuron paper. I think. I don't know how good that paper in terms of reproducibility is. So there's a paper. I think I forget who's on the paper, but I don't know if it's Ilya or somebody else. But there's a paper where Alex. Alex. Well, Alex is very. Doesn't matter. Alec Radford or
yeah.
Okay. Yeah. So yeah, I think that one is using unsupervised pre-training, stuff like that, and I think they do sentiment analysis with deep networks. But I'm not an NLP person. I don't know what this. I know that word embeddings are a big thing in NLP, and they certainly use deep networks for that. I don't know what state of the art for sentiment analysis is. Yes.
Do you have any research that on natural learning
is there any research on manifold learning and sort of label propagation for semi-supervised learning? Yes, and I think maybe is it like Target Prop or something? There's a couple of these like papers. I forget by maybe Joshua. What's the question?
Successful? Or?
According to those papers, yes. Are they used widely? No. Yeah, the question was if they're successful. Yeah, I'm not really aware of like very widely used in practice semi-supervised learning methods. I think it's a very active area of research in terms of. I think it's sort of everyone wants it to be solved in some way. The manifold sort of hypothesis is an interesting one. I think the book also covers it a bit. One of the hypotheses for semi-supervised learning. Yeah.
Is there a difference between natural learning and representation learning? They seem pretty similar.
Well, manifold learning is a subclass of representation learning. It's a type of representation learning. But I mean, you can have like the smoothness prior is one way to kind of achieve representation learning, or stuff like that, right? I mean, so manifold learning is a type of assumption, right? And they're not necessarily always mutually exclusive. But representation learning, I think, is more of an umbrella term for all of these things.
So would you say there's like a theoretical limit to how you can create a network, or are the constraints right now mostly technical in terms of like difficulty of training?
If the question is there any theoretical limit to how deep a network can be? No. I don't think there is necessarily. I think there's some. I mean, there's theoretical limits in terms of like. Depends on how much data you have, right? If you have infinite data, you may want a very deep network. And infinitely sort of, or if your data has very complicated, or the data, if the data, I mean, if the problem that you're trying to learn with these networks is very difficult or is very nonlinear, maybe you want a higher and higher level kind of representation. I'd say in practice, there's a bit of like, unnecessary competition between like adding thousands of layers on top of ResNet or something. But I'm not sure that's really necessary. That's more to show that, I guess, it works rather than it helps. So, yes. Whoever was first.
I have a question from online. It's about how much unsupervised retraining is necessary, and what do you see diminishing returns?
How much unsupervised retraining is necessary? Well, clearly the answer right now is none. I think you would see diminishing. No, I mean it's this. You would probably see benefits if you're doing like zero-shot learning. So if you truly have like almost no labels or one-shot learning, you would definitely see diminishing. As with any semi-supervised method, you would see diminishing returns as soon as you have more and more label data. The problem I think is that for a lot of these semi-supervised methods is that more and more label data means actually quite a small number of labeled examples. So you can get very far on like CFAR 10 with, I don't know, 50 examples per class or even less, 20. And that's in practice, that's not a lot. If you're actually like solving a real problem and you want to collect data, 20 labels this is not that much.
Any interesting avenues of research you've seen this year? And what are top 3 most exciting?
Top 3 that I don't know. I'm a big fan of domain adaptation, so that's what I'm doing these days. So specifically sort of unsupervised domain adaptation. So you're trying to learn something on some sort of source domain and without any labels in the target domain, maybe you have unsupervised examples, try to apply that classifier. And more generally, sort of, I think adapting sort of, this kind of lifelong learning of like adapting to newer and newer situations every single, without kind of, completely retraining your classifier. I quite like, there's a couple of these, in this line of work, there's a lot of this, there's a paper from DeepMind, progressive nets. I think a lot of research in there is to how to make those models that do multitask learning and that learn one task at a time, not grow with the number of tasks over time. Maybe you can make them shrink. As you gain more experience, maybe you can relate some tasks to each other, and shrink a model rather than sort of constantly grow it over time. Messaging networks, that's close to that as well. Yeah, there's a few of those. So there's all this like sort of one-shot or few-shot learning, learning from very few examples or adapting to a new domain. I think that's the sort of current thing that occupies my mind and I find exciting. And of course I find that exciting because I work on it. From the stuff that I don't work on, nominally I'm in the Google Brain robotics team, though I don't do any robotics. And there, I find robotics as an exciting field, but it's very hard, so that's why I don't do it. But doing sort of deep learning, like having these like agents that interact with the real world, and sort of learn to pick up things or move things around, that's very exciting, but again, very hard. So.
Is there interesting work on learning to clustering?
Learning to what?
Learning to cluster.
Is there any interesting work on learning to cluster? Yeah,
like image segmentation, but without graphs
I mean, there's been sort of questions about like image segmentation and can we do sort of generic image segmentation? You mean like sort of super pixel style kind of? Or?
Yeah, so not like labeling, but segmentation.
I think that people have done is in the same way that like they learn these like class agnostic bounding box proposals that I think people have done. Forget I think Facebook research or whatever. They have this like you have these like class agnostic segmentation masks, right? So they learn they basically collapse all. They take like a data set like MS Coco, take all the segmentation masks for a given image, and put them into one, or each of them as a proposal. So they learn to propose how objects are segmented in the given image, but without any particular labels. So people do that, but I think more as a pre-processing stage for something which will ultimately decide, oh, this is a tree, or this tree pixel, or this cat pixel, rather than or just segmenting it around the edges, or whatever you're trying to do. Actually, I'm not sure.
How much for just generate data?
Yeah, I'm not sure there's like a particularly. I mean, it's fundamentally what you're asking if there's a generic way to do clustering of data, and I think basically that means is there a generic way to do unsupervised learning of data? I don't think we have that. I mean, that's sort of what it boils down to. I mean, automatic clustering is essentially learning some feature space in which meaningful things are clustered next to each other. And that's essentially, or semantically close things are clustered next to each other in that representation. And that's basically the key question about supervised learning. How do you do that? How do you learn such a space? All right.
Thank you so much for coming. We'll be going to town hall, as per usual. It's a block and a half away from here.
I want to ask you something about this. One second. Talking about here when they're differentiating between a half space and a half plane.